Hello guys, welcome to another video. In this video, it's another tutorial video, but this one it's gonna be on this problem. Now, this is the first problem in IOI 2022 day 1. So I believe it is the easiest problem that year, but nonetheless, it's still quite difficult for me, so I thought it would be good to go over. The interesting thing is that this is actually a direct follow-up of a recent Q4. And that Q4 is none other than this one. So I did a video on this. It is literally the same except the constraints are much higher. So I'm not going to go over this problem. I'll just be explaining this. And I'll not go over this too much. If you want to get a precursor of the ideas I'm about to explain, I highly recommend you watch a video where I explain this problem. You'll find it on my YouTube channel. But nonetheless, let's get into it. So, first I'll quickly go over the constraint. So, in this Q4, you have n up to 100, but here you have up to 100,000. And the number of points that has a positive value, or number of cells, I should say, is up to 300,000. Whereas here, you can basically treat the entire grid as having a cell or not, because you can go through the entire grid in a fast enough time. But here, since the grid is very big, you can't have 100,000 squared cells. So they give you a point explicitly, and you're given their coordinates and the value. Alright, so I'll kind of go over Q4. Again, I'm not going to go into too much detail. So let me just draw some numbers again. So if we have 0, 1, 0. Oh, that's a terrible 0. Let me just make up some numbers just so that we get an idea of what we're talking about. So 15, 20, 0, 0, 5. All right. So the one observation you have to make is that when you take a value, it actually takes a form of a mountain. So if you were to draw out the black border like this, right? Now this entire section is color black. I'm explaining this in the context of Q4. Q3, they explain it differently with the piers and fishing, but I think explaining it with Q4 semantics is quite a bit easier to understand. And of course, again, when we have this, the value we get are these. And right now we get total of 5. So the observation is that this is a mountain. Now, if you were to, for example, draw like this, you can see we have a mountain of taking this value, this value, this value, this value. So what happened is our mountain has a step going up. Oh, I should not draw that too there. So it went up and it went down, right? And there's really no restriction on how it goes up and down. So for example, you can go up like this one at a time. Just making sure you're not taking the same row more than once in your little mountain in one direction. You can go up like this, going up 2, 2, 1, and so on. And the same thing applies for going down. So you can, of course, go down like this, right? And you go down. Now, each mountain consists of going up and down. And I will quickly prove to you why you can't have a, well, I should not say you can't, but it's not really optimal to have a mountain going like up, down, up, down, up. Why can't you have a mountain like this, right? Why can't you have multiple spikes? And the reason is because if you consider a number like let me just draw the sequence. So we have a 2, 6, 10, right? 3 and 5. So what happened is again, we went up to here and we went down and we went up again. So my claim to you is that we should not have, well, actually, let me just draw one more number. 10. So again, we went up, we went down, and we went up. Again, my claim to you is that we should not have this down. No, why? Well, you see, if you were to kind of draw this out in terms of black cells, it might look something like this. And it went down, it went up, and up. So you can see that by having this cell here, these black region here, you're blocking unnecessary numbers. Because right now, you could be getting these values, right? Because they're adjacent to a black cell. But you could have gotten these values. You could have gotten this value had you erased this. Well, you know what I mean. So you can just, but you could have gotten this. So it's unnecessary to have this here. So what that means is you can't go up, down, and suddenly connect to up again. So this proves the fact that mountains are separated. Like once you go up and down, that's your mountain. Don't bother trying going up directly again. So that is the quick non-formal proof. So now let's get to some cases we have to. Well, I should explain how we form a mountain. So again, the way we go up, or the way we go up and up and up. Now, the one restriction we have with this is that we can, like, if we go up here, we can't count this as the answer. Because technically, if we try to plant a black cell to the right, well, there's no cell here. So, like, we can update our states, but we can't count this towards the answer. Like, it's like we keep track of the best currently and the actual answer as two separate variables. And kind of the same thing applies with going down. So if you were to go like this, right, we go down. Well, there's no cells to paint on the left to go down. So this one doesn't work. So you again, you can keep track of this in another variable, but you can't count it towards the actual answer. So that means when you go down, you can't count the answer at column 0 towards the final answer. And the same thing with going up, you can't count the answer from the very last column towards the answer. Now, there is a few configurations I got to explain. So if I have the optimal configuration where I take single columns, or something like this. So is this mountain going up? Is this mountain going down? What do I consider this as? Because there's no change. It's just one column. So in my code, I consider this as going up in a single column. And this is also going up single column. And I don't consider this going down a single column because I already handled the case where there is one column that's going up only. So that's kind of the consistent thing I use to handle these single columns. And the other constraint I got to explain, if I forget, is the fact that if you go up, right, and you want to go down, you need to be separated by you need to you need to be separated by at least one column. That's because, you know, you need a black cell and you can't really kind of join the up and down directly. So you have to keep in mind that going up and going down, like you transition to down, like if you're at this column and you're going down, you have to look at things, you have to look at these columns, not this column, not the one before it, but you can look at everything else before. So yeah, and then I guess the one final configuration I can explain, since we can have mountain going only up, we can have this, right? You know, this is just going up. It doesn't necessarily have to go down, but it has to go up. And then we also have, like, yeah, that's pretty much it. So to recap, we have we have mountains. Now, here's how we do the DP. So the idea is, if I were to take this value, let's say I'm going up. So we handle up and down separately. So I'll explain the up part. You can kind of apply the same logic for going down, except I'll add a few little things. So if I want to take this value, what is the best mountain for me to join, right? Is it this? Is it this? Or is it this? By the way, these segments of going ups can be separated because you can draw the equivalent of the black cells like this, right? So yeah, they can be separated. So it's kind of like asking for these rows, what's the maximum answer, right? Because yeah, that's pretty much what you're trying to find. Because you don't care which columns they are. You just have to find out what's the maximum answer to join this to. Now, there here's where it gets a little tricky. So in Q4, the way you can solve this is say, because remember, you're keeping, so the idea of how to keep the DP is, so DP is equal to proof call answer. So this DP always keep track of proof columns answer. And it can be any column before 2. So that's the idea. So we don't have to go back to look through all the columns and try to figure out which row to do, so on and so forth. This DP always keeps track of the answer for any row for any previous columns. So in Q4, you say, okay, I want this. And I basically want DP of this row. So so if I were to label numbers, right? Again, this is By the way, this is upside down. Like realistically in the problem, the mountain is like is flipped upward. So it's flipped upside down. But I figure it'll be easier to explain if you view the mountain starting from the bottom. So again, I want this value. So I want dp of, so this is row 1, 2, 3, 4, 5. Actually, let me flip this too. If I flip one thing, I might as well flip everything to keep it consistent. So I want dp of 2 plus 4, right? This will give you the best answer for going up a column, at this column, up to row 4. So again, let me write it a little smaller. So 1, 2, 3, 4, 5. I'll just keep this in mind. So next dp of 4 is equal to dp of 2 plus 4, right? So you try all the ranges of the rows where you take the sum of, and yeah, this gets you kind of the overall main recurrence relation. So this is the main idea. And the same thing can be applied for going down, right? But there's one configuration we have to catch. So that is, okay, you know what? I'm drawing this numbers for the third time. So how do I catch something like this? How do I catch something like this? Technically, this is possible, right? Because remember, we can draw a black cell like this. And I know like this technically includes this, but I'm trying to show the point of how you can like join these two mountains together. So how do you join this? Because one, this is not at the previous column. It's at the previous column. And two, it's higher. So it doesn't have to be this. It doesn't have to be. It doesn't have to start at this row anymore. So what can we do? Well, we keep track of previous best answer. We keep track of previous best answer. So now our dp is, so ndp for is equal to max. Oh, that's a bad m. Max brief answer of going up, and dp of 2 plus 4. Yeah, so previous answer. So at any, so from column 0 to previous column, get the answer at any height, and you just join the mountain. So this is how you catch this case. And that's pretty much all the cases you have to catch. And then here, it's actually, it's kind of funny because this configuration, you can say the same thing. It handles this too. So if, let's say if this goes down, right? This goes down. Well, Okay, how do you join this segment that's going up? Because remember, it still has to be separated by one column. Then wait, isn't it just brief answer again? And it is. It is. So yeah, so no, this handles both one by one columns joined each other, and then going up and down. This handles both. And of course, you know how to handle like joining downs. So you will say, for example, here, you say NDP of 2 is equal to, okay, maybe I should include this 5. So you say NTP of 5, well, row 1 is equal to DP of 3 plus 5. Right, so you're looking at the rows you're taking. You look at the highest row and you add 1. So that's the index for your DP. Now, obviously, for the DPs going up and down, you keep them separate. So this is a main idea of what you're trying to do. This is not efficient, but it gives us an overview of the goal we're trying to achieve. If we can achieve this efficiently, we've solved the problem. That's, it's easy to achieve this in Q4 because you're allowed to go through every segment of roles where you're taking. So you can go through, you can try this, you can try this, you can try this, you can try all possible pairs of roles, which you include, but not here, not in this IOI problem. And let alone we can't have we can't exactly have what's my states? Yeah, we can't do and have a 2D DP. We can't. We have we have to do something linear. So if we can't naively try this, if we can't naively try pairs of roles, what can we do? Well, first you go up. So let's say you're, you're trying to figure out the DP for going up. So you try this row, you try this row, you try this row, you try this row in order. And I'll kind of explain why doing this is significant in a second. Let me try to think about it a little bit. Okay, so okay, okay, I got it. Got it. Guys, trust me, I got it. So let's say we're here, right? Let's assume we've processed these numbers already. So we're processing them in increasing row order. So what we do is we keep track of the running sum. So right now, the column sum is equal to 8. No, I'll just write like I'll just write sum of C. I have no freaking idea. So you say, okay, at this point, what is the best number for me to add this with? And let me explain to you a challenge real quick. So now what we can do is we can keep track of a row DP where it spans the entire row. So our DP is over the rows. So if I want to figure out the best answer between these two rows, I can have a segment tree that lets me query the range of the rows I want. 2 or 3. So this is what's going to help us. Now, we're not done yet. For example, let's say I want this DP. Like I want this row, right? So we have DP2. Like I'm going back to manually indexing for 1 second. And ideally we should be adding 4, right? Because if we take this row, that means we need to add these two values because these two values are not in this row. We're joining it. So, but the problem is we're keeping track of a running sum. So we're actually adding dp of 2 plus 8. And this is not valid because it's impossible for us to go up like let me erase this. Go up like this and go up. So take these values and take these values. Like it just doesn't work. You can't draw the black cells for this configuration. It has to be like this and then these two values. So the question is, how do we take into account for each DP, but somehow remove, like if I have this DP, right? So this is DP of 2. I kind of want to say like I kind of somehow wrap this in a -4, right? To cancel out these values. Then I can safely add 8, which is our column sum right now, our current sum. So this works out to be of dp of 2 plus 4, which is exactly what we want. So again, you have to be careful about this because we can't just go through each dp index and say, okay, this dp value, it's -4. Like we can't say this is -4. This dp value is going to be -6, right? We can't do that. We don't have the time. So this is where, let me switch to another column to better demonstrate this. So say we want this 5. I won't be demonstrating on this column because I just want to show something. You'll see. So dp of 1 is fine, but dp of 2 and dp of 3, they both need a, oh, let me change this number. Change this to 6. So these both need a -6, right? Because when we just including, when just look at this number, we don't have any issue with the sum. But as soon as we go up here, right, we got this value, but then we're adding this value, which we want to exclude. We want to exclude the 6. So how do we say for these DP values we want -6 without going to them individually? Well, whenever Oh, sure. Let me draw this 6 again. I swear. So we basically want, so we want to query the max value between 2 and 3. We minus 6, right? This is what we want. And notice that for each time we want to try something, we basically want to say 5 plus some max value, which which is from DP. So instead of trying to go through each row and find the appropriate cancellation of the sum, we can just update this sum max variable. So we can say um so let's in my code I have this variable called mx. So if we were here, right, let me color code this. Let me just color code this. So if we were here, it would first be query of 1, 1, minus 0, right? It's okay. We just have to look at rows 1 and we see we don't have anything to cancel out. But when we look at 5, then it becomes query of 2, 3, minus 6. Because as soon as I include the 6, like as soon as I try these, if I take in these DP values, well, I'm up here and I need to have this 6 removed. So I add a minus 6 here. So that when I add these two values together, sum plus mx, I won't be over counting or counting invalid things. And now if I were to go up here, well, now we have query of 4 and 4 minus 11. Because again, if we were to take this DP, we can't take these values, right? We can't. We should be adding only the 4 onto the DP. So if you notice that this is actually the previous sum. So at this point, like we go up, we can see these intervals are right next to each other. So this is actually like let me denote this as, so if current row is equal to R, so we have previous row previous R minus 1. This is the range, right? Where row 2, the previous row, well, at the start we say 1, and then we have R minus 1. So this is the range we're querying. And then for 4, you can see the previous row was 2, 3, 4, 4. So again, this by keeping track of this in one variable, we only ensure that this variable has to be correct, and yet it has to be the maximum value we add to the sum. And remember, our sum is a prefix sum. So for some DP values, we will have to cancel part of our prefix sum to not count invalid things. So it turns out this is the optimization. We only have to go through each point. Like we will go through all the cells that has a positive value, but we only need to go through them column by column basis, and we're not visiting all these extra zeros and whatnot. And we're able to apply the appropriate cancellation sum from the DP values to maintain the biggest answer for us to add to a prefix sum. So yeah. So this is the optimization. So that means this is a seg tree DP. And you can apply the same exact thing by going down. For example, if I'm here, well, I know I could take this, but then I would need to remove these two values, or I need to remove 35. So it would be like dp2 of 2 minus 35 plus 40, which turns into just plus 5. So it can apply the same appropriate logic for going down. Now, again, to catch the configuration where you have single rows, right? You have you go up like this and go up like this. So this DP value is not the previous. It doesn't have the previous column's answer. So the key insight here is that, like, if I were to start in a mountain and I want to look at any mountain 2 columns before or more, I might as well just take all the column, the entirety of it. And you can obviously see why that's true, because that would include the most number of things. And so Max actually starts out with previous answer of going up. So I hope I explained this well enough. So let me go over the TLDR. So TLDR. So we need to use mountains of up and down. And then we need to use prefix sum and going and I should say iterate rows of each column in order. Now, what does this guarantee us again? It guarantees update mx. We can update mx this way. We go by we query increasing ranges of rows. And with this, we also have the previous sum, which you can apply appropriately to the answers. And yeah, that's pretty much it. So I guess I'll go over the code a tiny bit. Tiny bit. So I have a sec tree. This lets me query any range for maximum value. So that's all you need to know about this sec tree. It's a iterative variant where you don't have to use recursive calls and it uses half the memory of a normal sec tree. So yeah, I kind of initialize I keep track of the cells of each column, and of course I sort it to go through in order. And I have two separate DPs for going up and going down. And don't worry about these parameters, they just make this segment tree do a range maximum query, which is what we want. Now here is the start. So this is a previous answer. Now the reason why this is so at this point, this current is the answer of a previous row. So this peaker is a previous answer. So here we're going up. So this is the code for going up. And this MX, oh, I forgot there's one configuration you have to catch as well. So if you were to paint the black cells like this, well, you can see that I'm going down and then going up. So these are right next to each other. Now, I know this sounds like something I literally disapproved. I said that you can't join the ups and downs directly. What I'm talking about is a black cells. Like if you were to go down with the black cells and go up with the black cells, yeah, there's no point because these values can be captured. That's why I have to separate these black cells like this. But in this case, it is the values being connected that are adjacent. So yeah, so we do have to catch this case. So this is going down and this is going up. So you can see in the code, this DP2, remember, at the current iteration, DP and DP2 are answers of previous columns. So I create a maximum answer. We just want a maximum. I don't really care where they end up. So yeah, and then can see I updated mx. So at this point, this sum variable I did not add the current value in. I added after, so this is the previous sum. I applied the appropriate cancellation with the sum. And the one thing you'll notice is I have these two vectors called apply and apply to. Because if I were to just update our DP directly here, well, it's going to affect the result of. Wait, maybe I don't have to. Maybe I don't. Because I was worried that if I update this DP here, and if I use the DP here, you would get the next best answer, which I don't want because it has to focus on the previous column's answer. So, but I forgot I do not use DP here at all. So I actually don't need this. So I can just say, well, actually, never mind. I still need this because I need to range query. I need to range query the previous column's best answers. I don't want to mess that up. So apply. So I actually updated DP after I completed everything. So yeah, I set up the grid. I set up the DP. I did exactly what I explained in tutorial. Keep the mx variable updated and apply the appropriate previous prefix sum so that when I add it, I'm not overcounting. And then I just kind of update the previous index positions and I delay the answer to be updated for later. And then this is for going down. You see, I don't execute it until I'm a second column because remember that I can't go down in the first column because there's no black cells to the left of it. But yeah, it's essentially the same thing. I just reverse the order, iterate through. So I go from top of the positive value in the current node to the bottom. I do the exact same thing. And this is just me using another index thing to avoid having to do if statements and such. But yeah, this is basically it.